Yeah, yeah, I'm impressed.
Noga will tell us about non-constructive methods in combinatorics.
Okay, thanks, and thanks for coming. So I'll talk about non-constructive combinatorics. Let me start by telling you something about constructive combinatorics. So I think it's fair to say that the vast majority of purely combinatorial proofs of combinatorial statements, they also provide effective procedures for solving the corresponding algorithmic problems. Well, when there is an algorithmic problem which is corresponding to the statement. And just to state some examples, and I want to stress that this is the case even when the statements talk about NP-hard invariants. So some examples that you probably all, or almost all know, is Dirac's theorem that says that a graph on n vertices with minimum degree at least n/2 contains a Hamilton cycle. And if you look at the proof, then actually the proof tells us how to find, to produce such a Hamilton cycle in the graph if the minimum degree is n/2, although in general deciding if there is a Hamilton cycle is NP-hard. I'm not writing these things because I'm not talking about this, right? I'm talking about the non-constructive parts. But another example could be Wiesing's theorem. So a graph with maximum degree D is always D+1 edge colorable. You can cover all the edges by D+1 matchings. And again, the proof provides an efficient algorithm to do so. The four-color theorem, if you want, is another example. The proof maybe is long and complicated, but still it provides a quadratic algorithm. Given a planar graph, you can find the four coloring of it. Okay, so, and this is usually the case with kind of combinatorial proofs. However, in modern combinatorics, we often use tools from other areas. And probably the most useful tools are probabilistic, algebraic, and topological. So with probabilistic techniques, still I think it's the case that usually the proofs provide at least randomized algorithms for the corresponding problems. And these algorithms are often efficient also. And when they are not, actually there has been quite some progress in recent years about making the non-efficient probabilistic proofs algorithmic. And examples include Lova's local lemma, for which we had more constructive versions or effective versions, first by Beck, then extended by many others. Then a major step was by Moser and Tardosh, and there are still extensions of that. And in fact, we'll hear more about that in this seminar by Jan later in this semester. Maybe another nice example is the 6 standard deviations result. So that's a result in discrepancy theory. Again, as I'm saying, this is only an introduction, so I'm not writing much, and I'm just referring to things. And again, there's the original proof, probabilistic. It was not constructive, but then there are algorithmic versions by Bansal and even more so by Lovet and Mecca. I could recommend the 4th edition, which is coming out of some book on probabilistic methods, which actually contains both these proofs, the Lovet-Mecca and also the Moser-Tardosh. Okay, but so this is about probability, but it's definitely less so about topology and algebra. So these methods, often the proofs they provide are non-constructive, and there hasn't been any real progress in making these proofs more constructive. So today I want to give you several examples of combinatorial statements proved by topological and by algebraic techniques. And in all of them, the proofs are non-constructive. Namely, we don't know any efficient procedure to solve the corresponding algorithmic problem. So this will be several examples. Some of them are very recent. Some of them are pretty old, but still, I'm not sure that that the old ones are known, and I think it's worthwhile. So what I want to show is the techniques that I believe are powerful, and also the intriguing question of trying to find maybe more effective versions of these tools. So the first example I'll discuss is, I'll call it the cycle and triangles theorem or conjecture. This is the cycles plus triangles. It was a conjecture first. Now I would admit that this is not maybe the most natural question to consider, but still it's a nice example. It has some history, as I'll tell you. And also, it's a nice example for me today because now I know both a topological proof for it and an algebraic proof. They are very different from each other, and both of them are non-constructive, and we don't know a constructive proof, so something that will actually solve the corresponding algorithmic problem. So let me tell you what this is. So this was originally conjectured by Du, Xu, and Huang, and a slightly stronger version was conjectured by Erdős, and this is maybe in the late 80s, so around 89, I think. And it says the following. So if we have a graph, so if G, VE, is a graph. No, he died in 96. 96, actually, yeah. So it's a, but as you know, he's still publishing papers all the time, so you could make conjectures as well, yeah. But this is well before, yeah. Yeah, this is right. So, and indeed, feel free to ask questions and to make comments. So we have a graph, and the graph has the following special form. So V is the number of vertices is divisible by 3. I denote it by 3n. And the edges, the set of edges is disjoint, or a union of two sets. They don't have to be disjoint, but it doesn't matter. So E1 and E2, where E1 is just a cycle on all the vertices. So E1 is a Hamilton cycle. So it's a cycle on all the 3n vertices. And E2 is a union of n vertex disjoint triangles. Okay, so this is n vertex disjoint triangles. So this is altogether a 4 regular graph, right? We have this maybe, if you want an example, I could have this, right? So I have a cycle, and I have also triangles, but it can be complicated. It's 4 regular because every vertex got 2 edges from the cycle, 2 edges from the triangle that contains it. So then there is always an independent set of size n. Namely, we can find always an independent set that contains one vertex from each triangle, right? Because if it's independent, cannot, like in this example, it could be these two, right? So it's one from each triangle, but it's independent also on the cycle. And this was a conjecture, but it was proved. So this was first proved by Fleischner and Stibitz. maybe around 93. And this proof is algebraic in the sense that, and I'll say something about it later. So it's based on some algebraic approach that I had in a paper with Mickey Tarsi. And the proof is non-constructive in the sense that we don't have an efficient algorithm. So I give you a graph, and this graph, I give it to you already with a cycle. I give you the cycle and give you the triangles. You don't have to find those. So you see that this graph has this structure. Can you find efficiently an independent set containing one vertex from each triangle and independent in the cycle as well? We don't know to do it. Okay, so yeah, so efficient I mean polynomial in the size of the problem, and I allow a randomized polynomial will be fine for me. So anything that you can write. Yeah. Okay, so let's say that open given such G, find efficiently, or can you find efficiently such a set, an independent set. Okay, but what I want is to show you a very recent topological proof of this, which I like and is also non-constructive. Okay, so I'll.
You should replace triangles by pairs, so matching a three-regular of that, and you have two vertices, then it's easier.
Yes. So. So you mean if it's a if the thing is a matching plus yeah, I think that then it's easier. I have to think about it a bit, but I think it's easier. It's definitely easier if you replace the triangles by k4s and you want an independent set of size n over 4, then it's also easy. But and then if you replace a cycle by union of cycles, then it's not true anymore. But if the length of each cycle is divisible by 3, then it's still true. But let's, but anyway, let's say. So I want to show a topological proof. And somehow I could have shown it really in a few lines. So it's a very short proof. But this is if I'm allowed to use some result of Scriver. And I don't want to do it because I want to show you the proof from scratch. Because there, then you will see how the topology enters. And as a bonus, I'll tell you, so we'll get also a proof of results of Lovas and Scriver about the Knesser graph. So this will basically be contained in what I'm saying. But at the moment, what I want is to show a topological proof of this. And it will be from scratch, well, assuming Borsuk-Ulam. So this will be the topological proof. So let me remind you Borsuk-Ulam theorem. So this was proved by Borsuk in 1933, and he attributes the problem to Ulam. Actually, the statement of the theorem appears before, even by Lusternik and Schnellmann, but basically in the 1930s. And it says the following, that for every continuous function f from Sn to Rn, there exist two antipodal points that are mapped to the same. Right? So at least x in Sn, so that f of x is equal to f of minus x. And the proofs are not so difficult, but they use topology. There are more combinatorial proofs based on Tucker's lemma. So it's similar to the proof of Brouwer fixed point theorem based on Sperner's lemma, but still I think it's okay. So this I'm going to assume. I said the proof is from scratch, but this will be the only thing that I'll assume. And there are several known applications or immediate applications of this. So maybe the best known one is the Hem sandwich theorem, and another very well known one, which is very easy consequence of this. And this is the version that I'll use, is that, so it's again Borsuk-Coulomb theorem, is that for every cover of the sphere, the n-dimensional sphere, Sn by open or closed, but let me write here open, it's true also if you write closed, by open sets, say, A1 up to an plus 1, so if you have only n plus 1 sets that cover Sn, then one of these sets must contain two antipodal points. So then there exists x in Sn and j between 1 to n plus 1, so that both x and minus x belongs to Aj. Okay. So we'll want to use these, and I'll also use some geometric lemma of Gale that I'll prove. So this is lemma, and this is due to Gale. And this is that for every m, let's say, bigger than 2k, we'll have two parameters, m and k. There are, so one can place, there are points, or one can place, say, m points, say, p1, p2, up to pm in S m minus 2k. Okay, so let d be m minus 2k, so that's a dimension. So we can put m points on the sphere, on this dimensional sphere, so that every open hemisphere contains k of the points. Okay? And moreover, it contains k of the points that do not contain this k, this set of k points, contains no two consecutive ones if we put them along the cycle with this order, p1, p2 up to pm. So I'll write it. So, so that for every open hemisphere, it contains k points, or maybe it contains a set of k points with no pi plus 1 indices modulo m. So with no two, it contains some specific subset of k points, and in this subset we don't have any two that are consecutive along the cycle. Okay?
That's not in the original guess, right?
That's so.
So without it, it's just Cartodori or.
No, I mean still you won't. I mean without it, somehow if you put the points in general position, then any hyperplane will contain at most d points, but still you have to worry that half of them are on one side and half of them on the other side, and for this you have to do something, right? Because so, and he can do it, and in fact and in fact he didn't care much about the second condition, but we will, but anyway, so even for that you need something, but here you have some extra condition, and this is and this is the proof is simple, so we will just I'll just show you what the points are. So we basically take points on the moments curve. So the proof is define what? So pi will be the point well, minus 1 to the I. This is to guarantee the sides, and then 1 I square I to the d. Right, we are in SD, so the number of coordinates is d plus 1, so this is this. And we want to put it on the sphere, so I have to normalize. So just divide by the norm, sum of I to the 2j. Well, j goes from 0 to d. So I'm not sure if you can see that, but this is just to make it a unit vector, right? Okay, so these are the points. And now we just want to see that this indeed satisfies the property that every open hemisphere contains a k of the points, and also with this. Okay, so I'll write it. Any open hemisphere. So first, what I want is I want to shift it a little bit so that it passes through d of the points. Always I can do it, so it's a hemisphere. And then I can start to rotate it, keeping it in the center until it hits one of the points. And then I keep 2 points, and I rotate it again, and so on. And I can do it until I contain d of the points, and no other point passed from left side to right side of the hemisphere, right? So this we can always do. Any open hemisphere can be shifted so that passes through d points.
Not the set, but the equate or passes.
Yeah, okay, any supporting, okay, any hyperplane. Any hyperplane, right, through origin. So this is really the supporting hyperplane, can be shifted so that it passes through exactly d points without moving any other point, any other pi from side to side. Okay, so let's assume that the supporting hyperplane indeed passes through d of the points. Now let's say equation, so the hyperplane, let its equation be a sum of a, or right. So d, because I started from 1. You mean the number of wait, what's the question?
Oh, sorry, it passes through the origin.
Okay, yeah, because the origin is 1 point, right? Yeah. So it passes through the. So right, so I mean, okay, let me do an example. So the equation of the hyperplane can be a sum of ai x to the I equals 0. I goes from 0 to d, right? So we have a x. No. Sum ai. I'm going ahead of myself. So sum ai xi equals 0. So this is okay. So it passes maybe let's write j. So it passes through pi. If only if when we substitute it, so sum of aj I to the j equals 0, and pj lies on the positive side. Yeah, and you see it doesn't matter. I can so the -1 to the I and the normalization do not matter here, of course, right? And the point lies in the positive or negative side of it, depending on the sign of this thing. Okay, so let's look. Here is a polynomial. So we have this polynomial. This is p of x equals sum ai x, or sum aj x to the j equals from 0 to d.
Maybe you want to call it q because of point.
Okay, so let this be the polynomial, and of course it can, the number of roots it can have is at most d, right? Because this is a polynomial of degree d, and it has among our points. So this is like the Moment's curve, only I now draw it in the plane, And we know that our hyperplane passes through exactly d of the points. So maybe this is 1 point, this is 1 point, and so on. And all the other points are somewhere. Okay. Now let's look how these other points, in which sides of the hyperplane they lie. So the thing is, so I may have several points here, right? The thing is that we took here -1 to the I, so they alternate. Among the points that are here, the squares are on one side and the triangles are on the other side, so they must alternate between square and triangles because the signs change. And now here, well, this point, it passes through this point. And here now, if you think about it, so now the polynomial change sign. And because the polynomial change sign, and here we make 2 steps, so the sign there stays the same. So here again, it will be the next point here will be a triangle, will be the opposite of this, right? Because the sign there is the same, but the polynomial change sign. And then maybe there was this point. Maybe here there was only 1 point. Again, it will be this, and then this. Namely, the points will alternate. And because altogether we have 2k points, so if it started by this, it will end by this. And we have exactly half on each side. Okay, so this is an explicit construction, and it just works. Okay, so we know this. And now we want to describe the proof of this proof of a cycle plus triangles theorem. Mm-hmm. So we have m points. On both sides.
You don't care about that.
Yeah, so I want to, I mean, there are a few on the middle, and I have on both sides at least k and at least one set of k points that do not contain 2 consecutive along the cycle. No, altogether we have m points. M points was, right, yeah, okay. Okay, and you see,
You can hope for, right?
yeah, yeah.
D of them may lie.
And you see, I didn't say it maybe, or I didn't stress it, but this picture also tells you that these points on each side, say the squares, are independent along the cycle, right? So they are, because we never took 2 consecutive ones. Right? So this is indeed okay. Good. So now we want to tell the proof of this cycle plus triangle theorem. So G is V, E1 union E2, V is 3n, is above, right? So or is on the left. So it means E1 is a Hamilton cycle, E2 is n disjoint triangles, okay? And assume that this is false. So suppose for contradiction, suppose that there is no independent set of size n. So we want to get a contradiction. Okay? So put points P1 up to P3n, my m will be 3n, on a S of 3n minus 2n, which is Sn, using a lemma, Gale's lemma. So I use the lemma with m equals 3n and k equals n. Okay. So and of course so that okay, let me identify P1, P2, P3n are the cycle, the Hamilton cycle in G in this order. So formally, I should have, I kind of identify the vertices of the graph with the points on the sphere. If you want, I could have said that the indices, the graph is on indices 1 up to 3n, and but we can live with that, right? Yeah. So really, the points are the cycle. Okay. And now, every now I want to define a cover of Sn by n open sets. In fact, n is less than n plus 1, so and the proof would have worked even with n plus 1, which means that actually I'm getting a bit more, but let's not worry about it. So in fact, we get here 2 disjoint independent sets, but let's just okay. So define a cover of Sn by n open sets as follows. So we have x for all x in Sn. I have to tell you to which sets it belongs. Okay, so hemisphere, well, there is a picture, so we have here this point x. There is the open hemisphere centered at x, right? And this, so for each x, open hemisphere centered at x contains an independent set in the cycle, of a size n. Right? This is just Gale's, the assertion of Gale's lemma. So we have here this independent set of in the open hemisphere. Now this independent set, at least for one of the triangles, it must contain 2 points of it. Because if it contains at most 1 point from each triangle, then it contains exactly 1 point from each triangle because it's of size n. There is no room. And then it would contradict the assumption that there is no such a. So it must contain some 2 points or more from one triangle, and this will be the color of it. So if it's triangle number 3, it will belong to A3. So must contain at least 2 points of some triangle and now of some triangle, say a triangle number j, and then we take x to lie in a j. So maybe it lies in more than one set, but it and it's easy to see that these sets are open, right? Because it means what? That I have this. So altogether, really, the definition of a j is that a point belongs to aj if and only if the hemisphere centered at this point contains at least 2 points of the jth triangle. And of course, that's an open condition, right? If I shift it a little bit, it still contains this. So this is. It's all of them, yeah. Yeah. For every, it's a covering by open sets, so they cannot be disjoint. I mean, definitely they intersect, right? So some x's belong to many of them, and therefore by Borsuk-Ulam, so you probably see the end by Borsuk-Ulam theorem. Some people denote it like this. So there is a x and x in Sn and j between 1 and n, because altogether we have n sets, x minus x belong to AJ. But that means that the same triangle contains 2 points here and 2 points here. So 2 plus 2 is 4, which is bigger than 3. I'm writing it because I think it's not common to have a proof that actually uses the 2 plus 2 equals 4, right? So this is, yeah. So this is a contradiction, right? So this contradiction tells us that indeed there is an independent set. And of course, you see that this proof is very non-constructive. So I'll repeat that it is open given such G. Right, but that it is open after this proof also. Find it's still open. Find such an independent set. Okay, so this is this topological proof. As I told you, really as a bonus, we get the results of Lovas and of Schreiber, and basically what I described is essentially the proof of Baran or of Josh Green of this Schreiber result. But it's worthwhile to say it because Lovas' theorem was maybe the first application of Bose-Coulomb for a combinatorial statement. So let me just tell you, this is just in passing, so something about Kneser graphs, because since we proved it already, it's a pity not to say it. So here is the definition of a Kneser graph for M bigger than 2k, kg for Kneser graph, mk is a graph. Vertices are just all subsets of an M element set, subsets of size k. So vertices are, I'll write it like this, M choose k. These are all subsets of size k of M, of a set of size M. Okay, and AB, so these are subsets, adjacent, if disjoint. Section B, if they are disjoint. So this is a Kneser graph. And then there is a version of this Kneser graph introduced by Schreiber. This is kg prime of mk. It's a subgraph of it. So this will be the vertices are all subsets A in M choose k. So again, sets of size k of 1 up to m that form independent sets in a cycle of size m. Okay, with no two. Okay, so independent in cycle 1, 2, and so on up to m in this cycle. So no two consecutive. Okay, and again, two adjacent, A adjacent to B, if and only if they are disjoint. So for example, you can check that KG52, this one is a Petersen graph. And kg prime of 5,2 is just a cycle of length 5. Okay, so this is
the vertices of kg prime are not.
So these are subset of the vertices of these. These are all.
The k elements are independent.
The k elements are independent in the cycle, right? So in a cycle of length 5. Right, to define kg52, we have to take a cycle of length 5. We have to take all independent sets of size 2. There are 5 of them, and they are adjacent if they are disjoint, and you can see that it's a 5 cycle. And so the theorem conjectured by Knesser in the 50s and proved by Lovas. In 78 is that the chromatic number of the Knesser graph mk is m minus 2k plus 2. The fact that it's at most m minus 2k plus 2 is easy, so you can color, write proper coloring. So for every I, which is small, which is between 1 and m minus 2k plus 1, you take all the sets A, the vertices are sets, so that I belongs to A. So they are not disjoint because all of them contain I. Okay? And then the rest is just all the subsets of the last 2k minus 1 elements, and they are not disjoint because there is no room. Okay? So plus the set of all A, so that maybe I'll try. Okay. So the minimum of A is bigger than m minus 2k plus 1. I guess here I covered it by independent sets. If you want the coloring, just take all the sets here so that the minimum is exactly I. That's right. Okay. And Lovas proved the lower bound, and Scriver proved the.
Maybe we want to stress that proving lower bounds on chromatic number is hard.
Right, yeah. Also, we will do sometimes, yeah.
But
okay.
It's not an
Right, yeah. I'll talk a little bit more about that in the second hour for those of you who will survive. We'll see. But, so the theorem by Scriver is that also this subgraph is also the same chromatic number. And in fact, Scriver also proves that this graph is what is called a vertex critical subgraph of the Knesser graph. Namely, whenever you delete a vertex of it, then the chromatic number drops by 1. This also is not so, this elementary, but not so simple. So one can think about it. But what I'm saying is that basically we describe the proof of both of them. Well, of course, this theorem is stronger, right? And we basically described its proof. And I'll not write it again, but see what did we. And this is really it's essentially Baran's proof. Nice proof. So the question is what? Is this the same Knesser who was a topology? Yeah, it's the same. And indeed, somehow you can see really, so it's not so surprising in retrospect that these graphs look like the Borsuk theorem. Somehow it looks natural, right? Because you kind of connect two things if they are antipodal. The two sets are the Hamming distance between them is the furthest away between all the sets. So somehow it's natural, and still it was okay. And I'm saying, so I won't write it, but I'm saying that we basically saw the proof of this because what did we do? So for the proof, you place using Gale. And as I said, this is essentially Baran's proof. Using Gale, you place m points on the sphere Sm minus 2k, and you do it in such a way that every open hemisphere contains an independent set on the cycle. And then you define a coloring or a cover by m minus 2k by m minus 2k plus 1 points here. So you assume that you have a covering. You assume that you have some coloring of the graph by m minus 2k plus 1 colors. And we want to show that this is not a proper coloring. And then you just define this cover for every point x. you look at the hemisphere centered at X, it contains an independent set of size K. This independent set has a color, and this color will tell you to which set it belongs, the point X. And again, this will be an open cover, so you will get two independent sets of the same color, and these are two disjoint sets that are independent and are of the same color. So it's really, and so really, as I said, the new proof of this cycle plus triangle theorem is essentially a reduction of it to the result of Scriver. But one thing I like about it is that so somehow Scriver or Lova's theorem, they tell you something negative, right? So he says the chromatic number of something is big, namely you cannot cover something by a small number of independent sets. And somehow the consequence you get from it is positive. Every graph of this and this form contains an independent set of this and this size. So it's a few lines, but still it's yeah.
These are
anyway.
the usual proofs of lower bounds for chromatic numbers by exhibiting a large independent set. Sorry, showing.
No. I think it's not. Yeah. So it's really, yeah. Really, yeah.
So even though it's
It's somehow, yeah. Somehow, so I like this proof not only because it uses the fact that 2 + 2 = 4, but so it's okay. So I still want before, I want to finish topology before the break, and then we will. So I want to tell you another combinatorial application of now it's a Borsuk type theorem. It's not exactly Borsuk-Ulam, but it's a similar fixed point theorem. And here I'll not show you the proof, but it's and again it's not constructive. So this is an old result. So it's something proved in the 80s. And K, okay, right. Maybe first say so some special case, K = 2 is essentially a theorem by Hobby and Rice in L1 approximation. Although they formulate it in a little different way, and was also proved by Goldberg and West. Maybe in 85. So this says the following. So I call it the necklace theorem. So let N be a necklace, well, an open necklace. In this necklace, it has beads of all kinds of types or colors. So it has KAI beads of type I. So it's just an interval of beads. Okay, I'll soon. So it has I'll soon draw a picture. KI beads of type I, and we have a I between 1 and T. Okay, so it's open, so it has something that looks like this. Okay, so then one can cut N in at most K - 1 times T places. So this will split the necklace into intervals, and a partition intervals into K collections each containing exactly AI beads of type I for every I. Okay, so we want to partition it evenly. So somehow the way to think about it is that maybe I'll say also this is tight for all kt. So the way to think about it is that you have a group of thieves, and they stole this necklace, but they are not just any thieves, they are mathematically oriented thieves, and they want to partition it evenly among them. But maybe the necklace itself, besides the beads, which are expensive, is made also of silver, gold, platinum, maybe even 1K. So it's made of some expensive material, and they lose some of the material whenever they do some cut. So they want to minimize the number of cuts. Okay. Now, finding actually the minimum number of cuts for which you can split it into equal parts is NP hard. That's not so difficult to show. But the claim is that always you can do it with at most k minus 1 times t cuts. The necklace could be very complicated. And this is tight because if, for example, the number of beads of each type appear consecutively along the necklace, then just to cut this part of the beads into k disjoint things, you need k minus 1 cuts inside here and k minus 1 cuts inside here and so on. So sometimes you need k minus 1 times t cuts, and the claim is that you always need that k minus 1 times t cuts is always enough. Okay, and as I said, here too the proof is topological, so it is some. And I'll say I won't show it, but actually, if you think about it, the case k equals 2, although that's not how originally it is proved, but k equals 2 is basically the ham-sandwich theorem, if you think about it a little bit. I mean, you have to place the necklace along the moment curve, maybe, but anyway, it's but somehow k. So proof is topological, and the steps. Let me just tell you. I want to say something about it. So the first step is something very simple, but still it's so show that the theorem for k1t and k2t implies it for k1, k2t. Okay, this is basic. This is very simple. So you split it to k1 collections, and then each collection you put it together and you split it to k2 collections. And somehow it's lucky that k1 times k2 minus 1 times t plus k1 minus 1 times t, this is equal to k1, k2 minus 1 times t. So if you think this is what you need, if you first split it to k1 collections, and then each of the k1 collections you split to k2 collections. And this is lucky because some of the topological statements, these topological fixed point theorems, they hold only for prime k. And really the topological statement is not true for things that are not prime. So the fixed point theorems that you use, so it's some Borsuk type. Yeah, specifically, yeah, I was using something of Baran, Schlossmann, Such, but there are several. So it's basically that some orbits are mapped into points, and imagine that groups of thieves would have these strong incentives to consist of prime number of people. This would be a disaster, right, for society. So this is right. So somehow this is lucky that it's okay. So this is the first step, and then there is another. So this is trivial, right? Another simple step is reduced to a continuous version. So continuous version, just that each bid is a measure. So this will be T measures. T measures on a necklace, on interval. So this is similar to those cake splitting questions that we have a cake, which is an interval. We have different measures on it, depending on how each participant is likes different parts of the cake, and we want to split it. And that's also a simple thing. So somehow you replace every bid by a small interval, and then you get the continuous version, and then you still have to worry about cuts that are in the middle of some bids, but it's not difficult to shift them. So to show that when you have cuts in the middle of bids, then you must have some other cuts in the middle of bids, because otherwise it will not give you an integer number, and then you can shift it. And then the main thing is that is this so prove continuous version by some fixed point theorem. So some version, some Borsuk type theorem. So so these are statements of the forms that when you have some continuous function from maybe sufficiently connected CW complex to a lower dimensional Euclidean space, and you have some free group action on the complex, then you have a whole orbit that is mapped to a point. So the Borsuk is when the free action is just that a point goes to its antipodal, and the orbit is 2 points, and here we get many. Because again, you can see that the proof is non-constructive. Can we find the cuts that we know that exist efficiently?
This is open also for cake.
Sure, yeah. So of course we want T to be big, because otherwise we can check all possibilities, but yeah.
Can you do something slightly not as good as P minus 1T?
Yeah, so I don't know anything that increases the number of cuts to any function of K and T that is independent of the length of the necklace. If you are allowed to depend on because the necklace could be very long, right? If you are allowed to depend on the length of the necklace, you can do something. And also, if you are allowed not to do an exact partition, but to do some sort of approximate partitions, then you can also do something. But if and as I said, so this works for continuous measures as well, and this is related to those questions about cake cutting, about which people in algorithmic game theory and before worked a lot. And some of theirs, they want algorithms. I mean, they are actually in the internet. I don't know, last year I think Ariel Procaccia talked here. So there are actually programs in the internet that will really give you some splitting of some things, because I don't know, you have to splitting cake is not necessarily a cake. It could be an apartment that several people rented together. Each of them has different measures of which room he likes, and they want to split the rooms among them so that something, okay? And then something, so they have all kinds of notions, envy-free, or you probably all know this very simple things, that how do we guarantee that each one gets at least 1 over the number of players of the size of the cake according to his measure. So you kind of move a knife continuously until the first one is shouting that he is happy, and then he gets this part, and then you continue by induction. And by induction, what's left is still has at least the required measure for everybody else. Okay, so for example, but sometimes you want partitions that are not only you want to get at least 1 over 1/3, let's say, of your measure if there are 3 players. You want to be sure that what you got according to your measure is at least as much as what anybody else got according to your measure, right? Because why, I mean, if the 3rd player is willing to give up everything, why should I suffer? I should get it, all right? So you want this, or you want, but but the splitting I'm talking about gives you the complete optimum of everything, right? Because we can split it. It's an existence theorem. You can split it so that everyone will get exactly the same according to each of the measures of every player. So if we could have done it efficiently, according to some allowed operations that we are allowed to do in these cake splitting algorithms, then we would be able to find really partitions that would satisfy all the properties that they ever considered. But yeah, but we don't know, and in some models it's not even known if for some of these problems you can actually find such a splitting with any finite number of cuts. But this is when you allow yourself only to produce cuts according to some algorithmic restrictions. So this was a little bit vague, but just to say that it's related to. Okay, so this is a good place to do a break, although I always hesitate to do a break here because people do not return. But let me just tell you, feel free not to return, of course. So what I'll do after the break is that I want to show something about a different proof of the cycle plus triangle theorem, which would be an algebraic proof. It's a very different proof. It's also non-constructive. And it's a method that gives other things, and in particular, it gives some results about graph coloring problems. And in particular, one thing I'll mention is related to the four-color theorem. And it's funny, but according to the abstracts I read to the lectures this afternoon, one thing I'll mention, again, I don't know if this will convince you to stay or not to stay, but one thing I'll mention will be sort of related to what we'll hear this afternoon. Namely, I'll have some coefficient of some polynomial that I want to show that it's non-zero, and they think, according to the abstracts, that this coefficient actually measures the dimension of some homology group. And if they would be able to prove this, this would give an alternative proof of the four-color theorem. But okay, so this is just. So we'll do as usual. We say that we take 5 minutes break, and then in reality it's 10 minutes. But in 10 minutes I'm really going to continue.
You're going to leave topology.
So I'm going to leave topology.
Can you at least state the application for like the constructs to the one?
Yeah, so I could, yeah. So maybe let me just say this, because I leave topology. So there are many other applications of topological tools, and this thing is about evasiveness, which is nice. So really many nice things. So here I want to talk mostly about things that the statement corresponds to an algorithmic problem, right? Evasiveness is not really an algorithmic problem, but there are other examples for that also. But still, somehow it seems that for statements that correspond to algorithmic problems, the most useful things are fixed point theorems like this. And also in the second hour, so the algebraic things, there it's even much more. There are lots and lots of algebraic applications in combinatorics, but I'll talk basically only about kind of one basic thing, which uses some properties of polynomials to derive some. And again, there are many other examples. Okay, 5+ minutes break. Simplest proof is by Josh Green, actually when he was a student. I think that was even before he was, when he was still an undergrad, before he was a student here. And there it's again the same thing that I showed here basically, but you don't even need Gale's lemma. You just put the points in random position on the sphere, and you are okay. You have to think a little bit, but let me not, like what you do if on one side you don't have Gale points, because then maybe on the other side you have many. So that would account to one extra color, but it gives, so to get the Lovaas statement is really the proof now is in a few lines. but you really don't need anything. You just need Borsuk-Ulam, and you and basically repeating what. But let me not do it. So so we want to talk now about some algebraic approach, and I want to start by showing you a different proof of the cycles plus triangles conjecture. Actually, that was the first proof, the proof of Fleischner and Stibitz. And the way I'll say it now, so I prefer to okay. So I'll tell you about a theorem that I call a combinatorial Nullstellensatz. So we'll see, and we'll get Fleischner and Stibitz from that, although they used really an early version of it. But anyway. Yeah. So this is right. Yeah. Yeah. So that's so this is something that I proved, and I'll first state it in a way that will not seem similar to Hilbert's Nullstellensatz, but then I'll tell you why it has this name, and why it is actually similar to the usual Nullstellensatz. So this says, and the statement here is very simple. It looks like, okay, let me say it. Okay, so F is a field, and P is a polynomial, a multivariate polynomial in the ring of polynomials with n variables over this field. Okay, so this is P. And suppose that the degree of P, the total degree of P, is the sum of Ti, I goes from 1 to n, where these are integers, but I'm stressing the fact this is a total degree. I don't mean here that the degree in xi is Ti. The degree in xi could be much bigger than Ti, but the total degree of a monomial is sum of Ti. And also the coefficient in P of the product of xi to the Ti, I goes from 1 to n, this coefficient is non-zero. So this is what we assume. Okay? Then for every sets S1 up to Sn, which are subsets of the field, and each of them is big, so let's say that Si is of size Ti plus 1, there exists Si, little si, and capital Si, such that the polynomial P, if we substitute it in S1 up to Sn, it is not 0. Okay, so it may look technical, but actually this is very simple and very natural, because if you think about the case n equals 1, it just tells you that a univariate polynomial of degree d cannot have more than d distinct roots, right? So this is somehow the natural extension. A multivariate polynomial, and you know that it's not a zero polynomial because of the assumption of this coefficient, it cannot vanish on a box, on a big box, and this is. Yeah, so it's no, yeah, yeah. It's I mean you can get it's related to Schwarz-Zippel if you want. You can get Schwarz-Zippel from that. It's yeah, it's a little bit hard. It's not hard, but it's a little bit harder than Schwarz-Zippel to those who know. But never. It was actually proved by Lipton, right? But anyway, Lipton and DeMillo. But anyway, yeah. Yeah. Okay. So so it's not. So just let me write it. N equals 1 is trivial. It's just the usual. And this one is not very difficult. Also, let me tell you something about the proof. So actually, there is an earlier version, usually I called combinatorial Nullstellensatz, both of them together. Maybe this one is better. And this is that if P is above, so if P of x1 up to xn vanishes over the whole box, namely if the conclusion does not happen, then actually it lies in the ideal. Let me not mentioned the word ideal. So then there exist polynomials. There exists some hi, which are also in the ring of polynomials. So that P is the sum of hi. I goes from 1 to n. So these are polynomials time a polynomial which is a product of xi minus s. S belongs to si. Right, so each of those is a polynomial. And I'm saying that if P vanishes over all this set, then it actually lies in the ideal generated by these polynomials, right? And moreover, not that it's so important, but the degree of each hi is at most the degree of P minus the degree of this, minus the cardinality of Si. So in my notation, this is sum of T, sum of Tj, j from 1 to n, minus Ti, minus 1. Never mind. Yes, somehow there are no cancellations of degrees. The total degree here. So you see, the usual Hilbert-Nullstellen ansatz is that if we have f, well, for Hilbert, we have to assume that f is algebraically closed. Here you don't care. And you have a polynomial that vanishes over all the common roots of an ideal. Well, the ring of polynomials is a Nether ring. Saying that it vanishes over all roots of an ideal just means that it vanishes over all the common roots of some fixed number of other polynomials. If this is the case, then, well, in Hilbert, not P itself, but some power of P lies itself in the ideal, namely have this form. So this says that if you are in the special case that each polynomial is a univariate polynomial with distinct roots like this, then actually you can say a bit more. You can say that P itself, not a power of P, lies in the ideal, and also you have something about these degrees, and then so this can be proved in a page or something, and to get this from this, you basically equate the coefficients of highest degree in both sides. So again, I'll not do it, but it's not difficult.
So if you know it's of small degree, then it must be the zero polynomial. Like if you know.
If I know that what is.
Degree is sigma Ti, and you assume that it vanishes, then it must be the zero polynomial.
So yeah, so if the total right, if the degree is too small, then it's a zero polynomial. That's the first lemma that you have to prove, right? Yeah, yeah, this is true, right? So if okay, so let's say let's believe this, and then actually we'll prove. But let me tell you something about so some remark, note. Okay, maybe I'll do. Right, so here is the definition. The aim is to prove still the cycle and triangle conjecture actually in stronger form, but let me tell you a definition by Sylvester. So we keep going back in time. This is from 1878 and by Peterson, 1890. So this is if G is a graph, and and V, the set of vertices is 1 up to n, just so you note it like this, the graph polynomial f of G x1 up to xn, so we have a variable for each vertex, and this is just a very simple thing. It's a product of xi minus xj over all edges ij, and to fix the sign is not really important, but let me fix it so that I bigger than j. So just take the. And they were motivated with questions in invariant theory. And in fact, I don't know if you ever wonder, so some of the terminology in graph theory came from there. Like, why is it the case that perfect matching in a graph is called one factor? And what is factor? What divides? So if you think about the graph polynomial, then really a perfect matching will tell you about some factor of it that looks, and indeed there are some notions in there. Okay, so this is a graph polynomial, and note that something that, okay, maybe I'll, depends in which order I want, okay. Let me first make one more definition. So definition G equals VE is a graph. Then I want to define the choice number of it. So it's some extension of chromatic number. So the choice number of G, CH of G, is a minimum K, such that for every assignment of a set SV, okay, a set SV of K colors, for every V and V, there exists a proper coloring so that the color, using the list, the color phi belongs to SV for every V. Okay, so again, yeah, it's not, if you haven't seen it, indeed, it's hard to digest maybe. So it's a minimum number K, so that whenever I give each vertex K colors to choose from, but not necessarily the same colors to each of them, then always each vertex can choose one color from its list so that we get a proper coloring. Okay? So if all the lists are the same list, this is the usual chromatic number. And because of this, the choice number is always at least as big as the chromatic number, and often it is bigger. So in many cases, it is much bigger. There are lots of results about this. This was introduced by Erdős, Rubin, Taylor. In 79, and in fact earlier by Wiesing in 76. And there are lots of results about Erdős, Rubin, Taylor. They show that the problem of deciding if a given graph is a 3, if the choice number is at most 3, this is pi 2 complete. It looks like pi 2, right? Because it's a statement of the form for every, there exists something. So it is and I suspect that among the, I never checked it, but I suspect that among the 3 authors, only one of them knew the definition of pi 2 complete. But it's, but this is, but anyway. So note, why is this a choice number of the polynomials relevant? So something very simple. Note, if, for example, a Si belongs to C, complex number, for example, or rational, I don't. Then there exists Si, I'm saying something trivial, there exists Si and Si so that the graph polynomial, when we substitute it, is not 0. This is if and only if there exists a proper coloring of G using the lists, right? Because the fact that the polynomial is not 0 exactly means that the difference between any two sides of an edge is non-zero, so they are distinct. And this is if and only if. So it makes sense that, And because of this, so maybe, yeah, still have time, so I want to tell you something about co-NP and BPP. So here is something. So therefore, for example, by a theorem, by this theorem prime, okay? So it follows that G is not 3-colorable. Not 3-colorable, that's a co-NP statement. Usually it's hard to show that the graph is not 3-colorable. If and only if fg, well, there exists some hi polynomial, so that fg is the sum of hi, let me write xi cube minus 1. I go from 1 to n. Right? So because this has 3 roots, the 3 roots of unity, of course, when we color, we can call the color any way we want. So here we color it by roots of unity, and it's so let me show you. I mean, it's a joke, but I think it's an instructive joke, so I want to show it anyway. I want to prove it to you. So here is a statement, proposition. Maybe I'll write joke because this is being videotaped, so I don't. So the proposition is that the chromatic number of K4 is bigger than 3. The complete graph on 4 vertices is not 3-colorable. Okay. Now I want to prove it to you. That's a co-NP statement. It's going to take a long time, right? So I want to show you a short proof.
Let me.
Yeah, maybe. Yeah, maybe. All right. So as I said, there are other proofs as well, but I want to show you a proof. As I say, I think it's still instructive. Something. So with this, we know that it's not 3-colorable if and only if the graph polynomial. Okay, so the graph polynomial f of K4. This is just the product of xi minus xj over all I less than j between 1 and 4. I don't care about the sign, so let me write plus minus. So this is a van der Monde determinant, right? So because of this, it's a determinant, so I can write here x1 cube, x1 square, x1 1, up to x4 cube 1. And then I can subtract the first row from the last row from the first, so this will be x1 cube minus 1. This will be x4 cube minus 1. And the others will be what they were before. And then I can expand by the first row, and then I get it as a linear combination, right? So it's x1 cube minus 1 times something. Yeah, well, there is plus minus somewhere here. Plus minus x2 cube minus 1 times this other determinant times and so on. And that's it, right? Because we have it as a linear combination with polynomial coefficients. And of course, you see that it's if and only if. So this is really a proof that it is not 3-colorable, because whenever you will substitute roots of unity in the right-hand side, it will vanish, and because of this, the left-hand side vanishes, and because of this, 2 of them are equal. So, and the same proof proves that any graph that contains a K4 is not 3-colorable, right? So it's even more. Now you'd wonder, so it's almost, right, suppose we want to get efficient algorithm for co-NP. We want to prove that a graph is not 3-colorable. We just have to show this. Well, maybe we'll have to use the polynomial identity testing, because we have to show that this identity indeed holds. But OK, so we only show that co-NP is in BPP. That also would be pretty nice, right? I mean, but of course, the trouble here is that in general, the HIs will be very big. So we will not be able to actually write down these HIs. But at least we could hope that in some special cases it will be useful, because maybe in some special cases we can, and indeed I try to show that indeed this approach can be useful for these coloring problems. It's,
this coloring, this special case for coloring, that K coloring is determined by the polynomials for K clicks, is in Lovas?
That's right, yeah. So there were earlier papers by Lovas, Lee, and Lee, and afterwards by also, I forget, or maybe one by Lee and Lee, and one by, okay. And they were a little bit more complicated. So they, but they also, they look about similar statements, that a graph has a clique of size something, if and only if the graph polynomial lies in some ideal, and some similar statement for colorability, not exactly with these polynomials, and but some statements of this form, which I think were never used to actually prove anything interesting. They got a complicated proof of Turan's theorem using this, but so you could. But still, it was indeed interesting because of the possible connection to these complexity classes.
Yeah,
maybe.
I think Lovas made it.
But that's right. Yeah. Yeah. So this is. Okay. So we want to say something about. So the theorem about the triangle theorem, and this is by Fleischner and Stibitz. So any G equals V E1 union E2 as in the left up board, right? So this cycle plus triangle, any graph. So not only is it the case that it contains one independent set of size n, in fact it is, and I told you the topological proof even gives two disjoint independent sets. In fact, it contains three. It is three colorable. And not only it is three colorable, it is even three choosable. Okay, you say three colorable. And even three choosable, even the choice number of G is most three. Okay, this is a. So we want okay, and we want to use this machinery. So the proof uses this theorem. Okay, so we had proof uses, but this we already saw more or less. Let me write it as a theorem. This is in the paper with Mickey Tarsi. So it says that if G equals VE, V equals N, E equals K times N, so the number of edges is K times N. Here it will be 2 times N, right, in this graph. And also the coefficient in this graph polynomial of the product of xi to the k is non-zero. If this coefficient is non-zero, then the choice number of G is at most k plus 1. Now this we basically, we saw the proof, right? So the proof is immediate from this combinatorial Dulce that I told you, because we look at the graph polynomial. The graph polynomial is of degree k times n. Okay, and then the coefficient, so all the ti's, okay, so maybe I'll write, follows from combinatorial Nullstellensatz with this ti equals k for all I, and the si's will be the sets of colors, right? So the sets of colors are of size k plus 1, and it's exactly this easy remark that I said, that there exists a psi in Si, so that the graph polynomial does not vanish if and only if there is a using the list. So that's essentially immediate. But we also said that this coefficient can be interpreted. So it counts something, interpreted in terms of orientations, of certain orientations of G. So I won't say it exactly, but you can kind of see that if you look at the product of xi minus xj over all ij in E bigger than j, then when you open it, every coefficient you get it means that for every edge, either you chose this or you chose that. So that corresponds to the orientation. If you choose this one or you choose that one, and you have to take an orientation in which the out degree of every vertex will be exactly k, if you want, say. And then if you count, if you want to count the signs, then you have to look basically at even orientations and odd orientations. So it can be defined, but that's not. Okay. And then basically the proof of Fleischer-Stibitz, which is not easy, is to show that this for G is above, this coefficient in K equals 2, the coefficient is actually 2 modulo 4. So it is not 0. They can. It is not so easy. So they have to. But it's a combinatorial proof by.
So n changes to be 6 seconds.
So n changes to be n is a number of vertices, 3n and right, yeah, and k is 2, number of vertices 3n. So because I don't want to write n is equal to 3n, but again, basically this. And okay, and that requires some work, but this is true. And again, kind of the obvious open thing here. Of course, again, we don't know it. This provides no clue on how can we color. So open. It's again the same problem. Can you color efficiently? Or can you find another proof? Can you color efficiently? And maybe even more difficult, can you color from the least efficiently? Well, of course, we don't know, right?
The choice number. So if you are given arbitrary set of
Yeah.
colors.
So now it will be this graph, and then you will get 3 colors for each, and you will try to color. Okay. So we don't know. But I still want to show. I promised to say something about the 4-color theorem. So I want to show a few other applications of this. Better to start here. Of this combinatorial null challenge as to coloring problems. Okay.
Okay, just one remark. Even though you didn't want Schwarz-Zippel or
Okay.
so, and you are talking about non-constructive, and if one increases the set of the size of the set from
Okay.
I don't know, ti plus 1 to 2 ti, then a random assignment, a random choice will.
Right. Yeah. So the Schwarz-Zippel lemma basically says that if we have a somewhat bigger box, then most points in the box are non-zero, and right. So then you could. Yeah. Maybe. Okay. So let me tell you something about other applications. I want to show two, but both of them I'll say very little about it. So one is, it is well known, so this is fact, Tate. This is a four-color theorem that every planar graph is four-colorable is equivalent to the following, that for all G, I'll explain, cubic, so 3 regular, all the degrees are 3. I'll soon write an example. Cubic, planar, 2 edge-connected or bridgeless. We cannot delete an edge and make it disconnected, or every edge contained in a cycle, is a 3-edge colorable. Namely, so what is a cubic? Well, here is a planar graph. Let's make it. That's right. But we already know about K4 many things. But I want some examples that can be big. So maybe this is right, planar, cubic. So some grid-looking thing, and I make it cubic, and it's bridgeless. Every edge is contained in a cycle. So you can color the edges by 3 colors, so that, or cover all the edges by 3 perfect matchings. This is and this is equivalent to the 4-color theorem. The equivalence is relatively easy, but I won't show it.
What does cubic mean?
So cubic is 3 regular. All degrees are exactly 3. Okay, so all degrees are exactly 3. And, okay, so the following is a stronger statement. I mean, we wanted, so with Mickey, when we had this thing, somehow we thought, so it's a new idea, we should try to prove the 4-color theorem. This is natural, so you try to, so we tried, and this is what we got. So what's the following theorem? This is stronger, so extension. 4-color theorem is that for every G as in fact planar, cubic, bridgeless, then in fact not only can we color the edges by 3 colors properly, but even if for every edge you have a list of 3 colors, you will be able to color properly using the list. Okay, so the maybe the shortest way to write it, but then I need another definition, but maybe most of you know, it's the choice number of the line graph of G is equal to 3. Namely, we can, so the line graph of G is a graph whose vertices are the edges of G, and 2 are adjacent if the edges touch each other. But what is written here in human language, it means that for every edge here I get a list. So for this edge I can color it either by 1 or by 2 or by 3. This either by 1 or by 2 or by 4. This either by 1 or by 7 or by, okay, and so on. And the claim is that I can always do it. Okay. And how does the proof go? So you look at the corresponding polynomial, graph polynomial of the line graph. You want to prove that the coefficient is non-zero, the corresponding coefficient is non-zero. And then you look at this coefficient and you try to interpret it combinatorially. And it turns out that this coefficient, so for this you have to work a bit, but it turns out that this coefficient counts exactly the number of proper 3 colorings of this graph, of the original graph, which is non-zero by the 4-color theorem, right? So, which is unfortunate, right? Because it means that we don't, yeah, anyway, it's a, and again you see, and actually, and this coefficient is the one that I told you that in the afternoon, the 2 lectures, if I understood the abstract correctly, they are talking about this coefficient, basically. And they, well, they wouldn't define it as this coefficient. They are talking about the number of Tate colorings of the cubic graph. And they hope, or they conjecture, that this coefficient is a dimension of some homology group, which they know to prove that is non-zero for planar graphs. But okay. So still, it's a funny proof, right? So you get it not by kind of the natural thing would be to try to say that the most difficult thing is when all the lists are the same list. This is not true in general for vertex coloring. It could be true as far as we know always for coloring of line graphs. That's called the list coloring conjecture. So there is a conjecture, but it's not known. And of course, because of the way the proof goes by this coefficient, then it doesn't provide an algorithm, right? So open, given such a G and lists, can you find a proper coloring? From lists efficiently. Okay, so again, the proof does not tell you have this graph. You have
Because how do you give those lists?
no in polynomial time. So I give you a planar graph like this. No. Here is a planar graph. Yeah, I give you. Here is a planar graph. So you get a big grid like that. So it's an n by n grid. And for each of them, you get a list of size 3. And then you try. So we know that there exists a coloring. Can we find one? I don't know. I mean, and just to find the usual coloring, it's just a 4-color theorem. So as we said, there is a quadratic algorithm. But here, and again, it just means we want a different proof. Maybe. I want to still go even back in time and show you an even earlier result. So that's one of my very first papers. So that's with Friedland, Shmuel Friedland, and Gil Kalai, maybe. Yeah, maybe it was. It appeared, I think, in '85, but definitely when we were students. So it, but took some time until it appeared. 19. Okay, and it says the following. So it looks very different, but I'll show you. Well, I erased the combination, but never mind. So it says that for every G, can be even multigraph, but never mind. So every graph, G, with average degree bigger than 4, and maximum degree equals 5, it contains always a 3 regular subgraph. Not spanning and not induced, just some subgraph, non-trivial, not with some vertices and edges, and all the degrees are exactly 3. Here's an example. I mean, I allow here parallel edges. So here is a graph with average degree bigger than 4, right? I added one edge. And maximum degree 5. So it must contain a 3 regular subgraph, right? Here it says. All the degrees are 3. And the claim is that this is always the case. And the proof was algebraic, but now I can say it because from the combinatorial notions that it's really in 2 lines. So let me show you the proof. Yeah, so the proof there was a little bit more complicated, right? But basically, if you follow it, it's a so the proof. Okay, so Okay, so I have a proof. We have this G equals VE. Let me denote V by N, and let me assume, so the average degree is more than 4, means that I have at least 2n plus 1 edges. I can throw edges and assume that the number of edges is exactly 2n plus 1, because that's enough. So the number of edges is this. And let me define AVE will be 1 if V belongs to E, and will be 0 if V does not belong to E. These are just the entries of the incidence matrix of the graph. And now here is a polynomial. We assign a variable to each edge. Okay. And this will be the product over all V in V of 1 minus the sum of A. Here I sum over all edges that contain V, so just this, and AVE XE, and I square it. Okay, so this, okay. So see, minus the product of 1 minus XE, E and E, and it's important to consider it over these 3, the field with GF3 if you want, the field with 3 elements. Okay, and we want to apply this combinatorial null-shell. So we will apply it with the SE. The set SE will be 0, 1 for all E. So what is the degree here? The degree of this polynomial, because of this term, is 2n plus 1. Right? So it is a 2n plus 1, right? Somehow I wanted, okay, good. Yeah, so 2n plus 1 is just the number of variables. Okay, this is the degree. And you see that this cannot cancel it because the total degree here is only 2n. So the coefficient of the product of XE to the 1 is non-zero because of what you see here. This will not cancel it. This is okay, and because of this, so our TIs are all 1, and we have here sets of size 2. So we have some non-zero assignment. Now this non-zero assignment, not all of them are 0, because if you substitute, so non-zero, okay, XE in E, not 0, right? So by combinatorial null-shell, that there exists. Okay. Now it's not the case that all of them are 0, because when all of them are 0, this is 1, and this is also 1. If all of them are 0, so it is 0. Okay. So let's see what happens if some of them are non-zero. If some of them are non-zero, then this part is 0. Now, if some degree here is not divisible by 3, then this modulo 3 is not 0. And by Fermat's little theorem, well, modulo 3, it's easier, but when you square it, it's 1. So the difference is 0, so then it is 0. So it cannot be. So really, all the degrees are divisible by 3. But if they are divisible by 3, then they are 3 because the maximum degree is 5. Right? So, so the graph is really E prime will be just all the E's, so that XE is 1. And then all degrees are divisible by 3, and because of this, all degrees are 3. And as you can imagine, of course, the question here, the open thing is, can you find?
All degrees are 3 or 0.
Say that again?
All degrees are 3 or 0, which is okay.
Yeah.
Yeah. So right, yeah. So it's not spanning, right? So some degrees are 0, could be 0, right? Yeah. Yeah. It's we saw in this example it was not spanning, so the degree here was 0, but the others were. So can you find such subgraph? Again, it's very simple. You get a graph, an input graph. You check the average degree is bigger than 4. The maximum degree is 5. You know that there is a 3 regular subgraph. Can you find it? We don't know. And in general, again, to decide if a given graph contains a 3 regular subgraph is NP hard, but here we know that it exists, and we don't know how to find one. So just I'll use 1 minute to say, I should say something about these complexity classes, right? So there were several definitions of complexity classes. Probably the best known is PPAD. PPAD, but in the old days it was called TFNP. So there was an early paper by Johnson, Papadimitriou, and Giannakakis, where they talked about the search problems where the decision problems are easy. So somehow you know that there is 3 regular subgraphs, you want to find one. And you can define, so this is what theoretical computer scientists do, right? Including me. You cannot solve a problem, so you define a complexity class, and you say that, okay, I cannot solve it, but you also cannot solve it, because if you could, then you could have solved many other problems also. That's right, yeah. Yeah, you could, right, because you worked on a different problem, you couldn't solve it, but if you could, then, okay, so there was this TFNP. Then Papadimitriou defined several complexity classes. Maybe the best known is PPAD, is when you get the existence of something by some parity argument, and the question is, can you find it? So I mentioned here several problems. You could wonder if maybe all these problems, the search problems, are indeed hard. Maybe they are complete for some of these complexity classes, or for some others, for properly defined complexity classes. Maybe they are complete. They are certainly complete for the complexity classes containing of them only, right? But maybe they are complete for a. And I should say that for both of these things that I mentioned, so these combinatorial null sets in general, if really you look at the problem given a polynomial, say by circuit, and looking at the circuit, you have to define it, but looking at the circuit, you know that this coefficient, the relevant coefficient, is non-zero, and you get sets SE. Can you find so this you can show that it's hard. So in the sense that what I could show is that if you could do this, you can invert one-way permutations. So you would be able maybe to factor integers or to do something like that. So in that sense, it's hard. Still, the applications are very specific. So it doesn't mean that any of them is complete for something. The same for Borsuk-Ulam or fixed point theorems. We know that in general they are hard. For example, computing Nash equilibrium is known to be PPAD complete, and this follows from some of maybe Kakutani, but some of those fixed point theorems. But again, we look at very specific applications, like the necklace theorem, or this triangle plus Hamilton cycle. Those could be easier. And in any case, it will be nicer, I think, to understand all of these problems better in order to understand, indeed, the power of those non-constructive, or at least so far non-constructive techniques. Okay, and that's a good place to stop. Thank you.